Hey everyone, how's it going? Welcome to lesson 8. We're gonna start off with Gaussian elimination today, and I'm not gonna lie, this one was a lot harder for me than I expected it to be. Um, I try to avoid this, but I actually ended up looking at some pseudocode to help me get through this, and I held off on that for a long time to try and understand and grasp it myself, and it was kind of stupid. My hang up, essentially, I was worrying about edge cases which didn't exist. um, I did a slight deviation because technically Gaussian elimination can be done on non-square matrices as well, because it's formally just the process of forward elimination then back substitution, which still works if you have more unknowns um, than equations, or the other way around, if you have more equations than unknowns. Um, the difference being that in that case, basically, you don't actually solve the system of equations. So yeah, I just did that because that was one less thing to worry about while doing this, and I'll try and comment on where my hangup was when we get to that point in the code. But it was a bit of a pain. You guys can check the behind the scenes video that I posted yesterday, which I posted 6-7 ish hours after I did the lesson 7 video. So I'm still counting it as a video for yesterday because I don't want a broken streak. Um, yeah, this one was hard, but I think it's okay. I think it was a moment for me that was difficult, and I had to resort to actually, not exactly because it wasn't real code, it was just pseudocode, and I knew what needed to be done, and I was fairly close. I was just worrying about something that I shouldn't have, and my pain point or my fault was I didn't do the same thing that I did in my matrix multiplication video, which is, write it out and do it on paper, because then I would have just, it would have automatically clicked why I'm having an issue with this, and it would have been fine. Anyways, but that's okay. And I feel like if whoever's watching this eventually gets to that point where there's something that's so difficult that they had to, in some sense, look up the answer. Don't just look up the answer, like, refer to some pseudocode, or even some regular code. Just quickly glimpse it for a split second, then try to do it by yourself. Is okay, it starts like this, and then what do I do? And then you think it through and try and get further, and then you come back and forth. So A, that, and B, realize that that's okay, and that just means that you're gonna want to have to go over it again at some point. Kind of fresh. I gave myself a fairly large break. I haven't actually done until earlier today, like a few hours ago. I didn't do any data science math stuff. I just gave myself the space from it after I figured it out yesterday. I did I think the second half of Gaussian elimination today, back substitution, which I'm not going to do in this video. That'll be a video for tomorrow. It'll be the wrap up for Gaussian elimination. Yeah, so when you get to that point, just go ahead and do it. Take some space and do it again, right? I'm lucky, so because I have a reason to come back to it again, because of this, which is really nice. It's just I'm oh, okay, I'm thinking about it, and now I'm gonna have to do it again. I honestly it's still fuzzy for me in my mind, so we're probably gonna get stuck a couple of times while doing this, which is sketch, but it is what it is. I'll make do. It'll be fine, right? So what is Gaussian elimination really? It's just a linear algebraic method or for solving a system of linear equations. It's basically that simple. It's really not much. And really what you're going to want to do is, given a matrix, right, you do certain elementary row operations. Elementary row operations are Essentially, you can swap two rows together. You can scale the value of a particular row, and you can add or subtract one row to the other to make a new row to replace that with, right? Um, that's essentially Gaussian elimination. And when you're doing it on hand on paper, you can use intuition to a large extent. Let me see if I can find an example I can showcase here. So, like for example, here, I'm just gonna see if I can highlight this image. Yeah, that image, right? You can see. So first, you want to do elimination. When you're doing the forward elimination, you essentially want to get the matrix in the upper triangular form, like in this animation over here. Hopefully this animation will, yeah, so where all the diagonals essentially are 0. You know, and you know, you can swap things around, like that's an elementary row operation right there, right? And here you have a row that's all zeros. That actually just tells you that there isn't a solution to the system of equations. Another way to figure that out before you get into the process of Gaussian elimination is to just figure out the determinant, right? Because if the determinant is non-zero, then that means that the matrix is non-singular, which means it does have a unique solution, right? So it's two negatives make a positive kind of thing. That's kind of how I tend to remember that, because it's a weird and confusing thing that we actually looked it up the other day. Like, why was the determinant necessary? Because if a determinant is non-singular, then it means that the matrix is invertible, and when a matrix is invertible, it means that a b equals x can be rewritten as x times a inverse equals b. So there's a solution there. I'd have to look up that particular. Let me see if I can actually find that now I'm thinking about it. Because I saved. Oh, allow. Yes. I had a. Oh, there you go. Allow. Why does determinant have to be non-zero for? Yep, there you go. Invertible matrices. If the determinant matrix is non-zero, then A is invertible, meaning there exists an inverse matrix A such that A inverse times A times A inverse equals the identity matrix. And for a system of linear equations represented by AX equals B, where X is the vector of unknowns, multiplying both sides by A inverse yields X equals A inverse B. Therefore, there being a single solution. So if A inverse doesn't exist, you can't do this, right? So that was why I remember that from the previous video, and that was a fun thing I wanted to revisit. So we're here. So anyways, this is essentially Gaussian elimination, right? You want to get the thing in upper triangular form, meaning the diagonals have to be all zeros, right? And then you do back substitution, which is essentially, for example, if you have, I actually had ChatGPT generate an example, so let me just show you that. I think I have a worked example here. So this is over here. It's called an augmented matrix, which in my code I'm just gonna handle separately as a regular square matrix and vector of the solutions. A vector of the constants, I mean. But they just have it combined because essentially in Gaussian elimination, anything you do on the matrix, you have to do also to the vector of constants, right? Otherwise, it just is, I'm just doing random things, right? So, for example, I'm going to start with this one, right? Now, I can clearly see that I can get rid of this 2 by just multiplying the first row, 1, 1, 1, 6, by 2 and subtracting that from the second one. That would leave me on the second one will be 0, 0, 3, because 1 times 2, 5 minus 2 is 3. And then 6 times 2 is 12. 21 minus 10 is 11. Minus 2 is 9. So this will be 9. So it'll be 0, 0, 3, 9, right? And then you could swap this one with this one because that, since these are two zeros, we know we can just slap that down as the last row. We can swap this row in the middle row. We can do things like that intuitively, right? But to do an algorithm for this, right? Because you can't put intuition, mathematical intuition, or any kind of intuition into code. Some people argue that point with the rise of AI and LLMs and all that. I still think you can't put intuition in there. It just is, and at the end of the day, probabilistic token generation. But still works. You have to look at this from the perspective of making an algorithm. Now, I believe somewhere over here. So this over here is what I really do. Everything it says here is pivot selection, identifying the pivot. The pivot element is essentially the first non-zero element in a row, and each pivot needs to be to the right of pivot from the previous row. So if your first row, first column, like the first item is your pivot for the first row, then the pivot on the second row needs to be at least on the second column, right? It could be further up, which could be possible in a situation where you're doing Gaussian elimination for a system that doesn't have a solution or something like that. Or, in the case where it's not a non-squared matrix, meaning it's got more unknowns than equations, or more equations than unknowns. Either way, in that situation, you will find that situation where sometimes it's not going to be the perfect diagonal, right? But that's the core of what a pivot element is, right? Let me see if I can even find the pseudocode. I had it generated somewhere. I think it was this one. Yeah. So this is actually the pseudocode for partial pivoting versus this, which is the main pseudocode. So normally when we do pivoting, you have to avoid division by near zero. That's why pivoting matters. Another thing about pivoting, especially in the sense of in computing, is because even if it's not zero but just really, really small, that can lead to some serious floating point errors that can propagate and reduce the numerical stability of the algorithm. Numerical stability meaning specifically, let me actually just Google that because I did look it up recently. Here, I got a Wikipedia page. Oh, is it in the same way? Oh, I already had it pulled up. I'm a dummy. It's essentially, let me see if I can find the specific line. Some numerical linear algebra principle. The precise definition of stability depends on the context. One is another algorithm for solving ordinary and partial differential equations by discrete approximation. Okay, wow, this is a lot of this. This is the problem with trying to learn math from Wikipedia. Sometimes they just throw so much info at you and are very specific with terminology that it's just can be hard sometimes to parse this. Let me see if I can. Yeah, the Google blurb is much easier to. Calculations that can be proven not to magnify approximation errors are called numerically stable. That was the one sentence I was looking for. That was difficult, right? So that's what these points 2 and 3 are about, right? And essentially partial pivoting, there's partial pivoting and there's complete pivoting or full pivoting, which is partial pivoting is just swapping rows, I believe. Look at column 1, entries 0.001, 1, 2, value is 2, swap row 1 and 3, right? Swap this row with this row, and boom, that's partial pivoting. Simple, you're just swapping out the rows. I believe with complete pivoting, complete pivoting swaps both rows and columns for maximum stability, and that's rarely used due to bookkeeping cost, which I'm actually not sure what they mean by bookkeeping cost exactly here. Just from context, I'm presuming it just gets hairy to manage during the calculation, both algorithmically and otherwise. Let's see if there's... Okay, never mind. Okay, I'm just getting tax stuff. Alright, never mind. But that's what I'm assuming they mean by bookkeeping costs. So let's jump into it, okay? I'm gonna start with a super simple piece of this is the swap. So I1, I2, A, B, right? This is a function I'm gonna call whenever I want to swap something. It's gonna be easy. I'm gonna swap in place, so AI1 equals AI1 AI2 equals AI2 comma AI1. Oh, sorry, I just put I2 twice. And then do the same thing with B. I1 B I2 equals B I1 B I2. Wait, did I do that right? I1 I2 I1 I2 I2 I1 for A. Okay, B I1 I2 B. Oh, I just did the same thing twice, so I actually meant to do that. Yep, that seems right. So that's your swap. Code wise, pretty easy. Okay. To get something, I'm gonna want to be able to return the column. Now, getting the column, we've written that code quite a few times, so I'm just gonna go I comma A colon, or actually I'll just say J. J makes me feel better. Hey bro, you want a J? No, I'm kidding. I hope that no one understands that. It'd be funny if you did. Well, it's gonna be our own happy little accident over here. That's okay. So, get call JA, so I'm going to return V for V in A J. Right? No, that's just gonna... That's incorrect. VJ, so for each row in A, we take the jth element and we squish that into a list and we return that, which is getting the column, right? Now the easiest way to determine the swaps, once again, if you're doing this intuitively, like it's just a bunch of like easy readable integers in like a 3x3 or even a 4x4 or a 2x2 matrix that you're doing on pen and paper, you can just intuit these things. To make my life easier, whenever I would just always get whatever the largest element is for a column and I'll swap it. That was just easier, made the most sense to me. So that's what I'm gonna do. Something seems to have bitten me. feeling a little itchy. So get idx max vec, right? So for a vector, return the largest possible value. Return the index of the largest possible value, right? Because we want to take that index and it'll probably pass it to swap to help make the swap, right? So for some vector v, we are handed a vector. And that vector, we'll probably get it using the get call function. I want to get the index of the maximum value of v, right? So we first get the maximum value of v. What's going on? Why is this not? Let me just restart extension host. I don't know, sometimes I feel like Pylance or something goofs up, I don't know. Yeah, that didn't seem to change anything. Oh well. Max, okay, so we get the value of the largest thing in V, and we get the index of that, and we return that, right? Except, what if it's a negative value, right? Or what if it's all negative values, right? And one of the negative values is negative 0.000001, right? In which case you'd return 0.0001. So that would not be the best. Here, if you hover on max, you can see that you can hand it key, which is a function, which max can use to determine the largest value, right? And we are just going to use that and hand in the absolute function, which just takes the value and returns the integer, returns the absolute value. So negative 10 versus 7, 10 would be the largest one returned in by this function. So these are some super easy starting point thingies that you'd need. Let's get into the meat of potatoes. Let's do f sub. I'm just going to call it f sub. It takes a and b. A is the matrix of coefficients, b is the constants, right? Yeah. I'm already forgetting how to do this. I just did this like yesterday morning too. This is rough. I'm a little upset with myself right now. I did it on video too. Right? Let's just go, say k max equals len a. Let's just say that. Let's go len b. We're just going to presume everything's a square matrix. Make our lives a little easier. Len a, len b, either way would have been the same. Right? Oh, that was a bad cough. Alrighty, let's do 4k in range k max, right? If, let's say, p colon equals get idx max vec, get call JA, right, for k in range KA? That doesn't seem right.
Are you done with your video?
No.
Why?
It's ongoing. I'm recording right now. It's okay. It's a happy little interaction. It's a happy little action. You wanna come say hi to my 0 viewers?
No, I look
No.
like shit.
You don't look like shit. You're my wife. I'm not married to a piece of shit.
Anyway, I have got my leave approved for Friday. I've swapped my leaves.
Okay, I might have to be on a call with Nawfal on Friday. So I don't know. I mean, I messaged him and I told him that. Anyways, let's get back to this, boys or girls. I don't know who's watching. So if P colon equals yes, babe.
Nothing, just focus on your video.
Then you're distracting me.
I'm worried.
Okay. Okay, so if P equals this, right? Right? We're gonna have to get that column, right? So for each entry, so every time, so K in this first iteration is the first row, first column, right? Then it's the second row, second column, third row, third column. So that's the column we have to get, right? A wait a second. Something seems weird here, right? What would be weird here? Something is weird here. We're gonna figure it out together, aren't we, guys? I believe in us. Because if I'm getting the column at K, right? For the first iteration, it's fine. But for the second iteration, which would be the second column, right? And the second row, because you're looking at the diagonals, I only care about the max item or the largest absolute value below K, not above. So if it's above, I just don't want to even look at it, right? Because we're done with that. We're only looking below. Right? Because the core is that, how do we do this? I'm just gonna look at what I did earlier. I even did the not a square matrix thing. Oh, okay. That makes sense. So okay. So essentially K comma space, right? And put IDX, oops, not IDC, IDX, max V, IDX colon, yep, that makes a lot more sense. So from this index onwards, so I'm at index K, or row K, column K, they're both the same. And I'm passing that to the get IDX max function along with the vector, which I'm getting from get column KA, right? And this, looking at the vector only from that index onwards to get the max value, but then gets the index from the full vector, right? Right? It's not like I'm doing this, because then I'd get the wrong answer. Or sorry, this. Ugh, I can't type. Right? You'd get the wrong answer that way. So we're not doing that. Okay. That was me cheating again. To figure it out. Okay. equals k, right? So this process might return the same index, which would be the case if all of the below values are either smaller than or the same as the current value. So if you get, so if it's not equals k, sorry, then we want to swap, right? So then we swap is in place, so I don't have to do anything about it. So I take k, the current index, and I give it p, the new index, and then I say, and then I just give it a and b. Boom and boom. Boom and boom. Boom, boom, boom. Right? Right. That's okay. So we've figured out the pivoting so far, guys. Pivoting is done. And it's all, I'm just trying to do it all from memory. I'm a little scared. So, what's the next step here? We're gonna have to actually do the forward substitution, right? Right. So, for I in range, start from k through till k max, k plus 1, yeah, that makes sense because we're gonna look k plus 1, the row after, right? Right, and let's make this k max minus 1 because we don't want to iterate over the last row, right? Right? And for I in range k plus 1, so we have to calculate the multiplier, right? Right? Now algorithmically, what is that multiplier, right? So if I have first row first element is 1 and the second row's first element is 3, to get rid of the 3 I need to multiply the original row k in this loop's context, by 3, right? Minus the next row, right? So that's the multiplier. Take the row minus multiplier times the original row, right? But how do we know algorithmically that the multiplier is 3? We can just blindly always do row k, the multiplier would be the element under the pivot, so 3 in this case, divided by the element at the pivot chosen, right? Right, so that makes sense. So we'll say m equals a element below the pivot, right, which is I in this situation, I, right? No, yes, I, I'm looking at I, and we're sticking with the same column, so k divided by a, the element, the current pivot, right? Right. Now, once again, I tend to have a bad habit that I really don't want to institute in people, where I just kind of go through all the logic and then I try to correct it, and it's like I'm so confused as to where the issue is. Always be testing it in small ways. Like right now, it'd be a great point to stop if you're doing this at home. Stop and just test and see that the multiplier is giving you is calculated in the way you are expecting it to be calculated, right? I'm just going to move forward, but there's something I want to say because really my goal here isn't to teach you data science math or coding or Python or anything. It's just teach you the ways of thinking about in an abstract sense that you can apply anywhere, really. I'm just choosing it to do it through this project, both for my own edification, um, primarily for my own edification, really. Um, and it always starts with curiosity. Being curious about things is really, really the heart of it. It is really where all of the beauty, all of the fun in learning lies, is having that curiosity. Anyways, so if I'm correct, this is the multiplier. I'm not going to look at my old code, but I will look at this. Oh, okay. AIK over AKK. So that is the multiplier. I is defined as k plus 1, which is where it starts at. Right? Right? And then we replace it by rho I minus m times rho k. Yeah? Yep. Okay. So rho I, because that's the row below rho k, right? So the second row, right? I keep going right. That should become my my motto, right? Right. So let's say a I. That's what we got to replace, right? We have to replace that entire vector with what? Let's say we just do for, let's define what we're gonna iterate over. We're iterating over AK, that's for sure. For E and AK, that's the elements, right? There's something small here that I'm immediately gonna correct, but I'm gonna pretend that I don't know that and just keep moving forward for a moment, right? So I'm gonna M times E, right? Okay, so M times E for E in AK. AK is the previous row, so the top level row, the row where the pivot exists, and we're looking below that, right? And we have to zero out the elements underneath the pivot on this row. So it's not just multiplier times the elements of row K. I also have to subtract that element AI, which leads me to the thing that I was telling you that I know about that I'm going to pretend I don't, which is we need to actually enumerate this and get the index, because we're going to do a I IDX minus yep, right? So in the ith row, the current row that we're checking out, the element at index, let's say for example 0, we take that value, whatever that is, 3, 5, 7, whatever, and subtract it with the multiplier, which is the element just underneath the pivot, or the element beneath the pivot divided by the pivot element, which is AKK, right? That's the multiplier. And we multiply it by that element and subtract that multiplied by that element in the row containing the pivot, and then take that away from the current element in the current row. Yeah? Yeah. Right? Okay. And then the next is BI. Right? I'm just going to do minus equals for that. M times bk, right? Right, so the element in B, we're gonna wanna, well, everything we did at AI, we need to do at BI. In what did we really do in AI? In AI, we took the elements in row K, which are the elements in row K, which is the row containing the pivot. We multiplied each of those by the multiplier, which is the element just in the current row, just below the pivot. The element in the current row that's below the pivot, divided by the pivot itself, or the chosen pivot, times that element, and we take that away from the element in AI, right? So we have to do a similar thing. We have to take M times B, which is the constant in the same position as the row with the pivot, multiply that with the multiplier, and subtract that from the current element in that row of B, or well, in the position in B, the vector, because it's a vector, B is a vector, A is the matrix, B is the vector. My wife just stepped out of the house. I'm wondering what that's about. It's past midnight, but I'm sure she'll be back soon. Yeah. I believe I can fly. I believe I can. No. That is it. Don't have to really return anything because everything is happening in place, right? Okay. Let's copy some. I had some forward elimination tests. Have these tests over here. These may not work because the thing is, the way I did forward elimination, I just kind of, oh yeah, forward elimination doesn't exist here. Oh yeah, I'm too lazy. I'm just gonna rename F sub to forward elimination. Should cause an assertion error. Yep. 2 by 2. It's right at the beginning. Jesus Christ. 2101. See, I know the problem here. At least I think I do. We're gonna open up a new cell. Right, we'll just do that. And then just look up A1. Right. Now, you can see that this is different from the expected value for 3, right? And why is that? Because essentially the generated tests here, and I wanted to showcase this even though I knew it was wrong. I did this live on the behind the scenes video. Is that even though our method of getting the upper triangular matrix is absolutely valid, the tests are generated using more of that intuitive method, and it's actually not even that intuitive. We could quite easily change this so that this only occurs if the current value is 0 or close to 0, and otherwise just continue as is. In fact, maybe we can just might as well live code that. But my point is, before I continue into live coding and fixing that, it's just me once again reminding you that, don't trust ChatGPT, right? Trust yourself. Trust your intellect. Trust yourself to know things, to understand that, like, oh, in this case the assert is failing, but there's actually nothing wrong, right? And yeah, don't trust yourself too much, because but don't always presume that the AI is correct, or that anyone else is correct. Sometimes people are wrong, right? In their description of things. And what's the difference here? Upper triangular can be getting to the upper triangular matrix can be done in any number of ways as long as it just involves the elementary row operations, adding and subtracting rows, multiplying them by some sort of, or scaling them somehow, or swapping them, right? These are your elementary row operations. And the reason mine doesn't work here is because I forcibly swap the row with the maximum, which in this case is the second row, or the top row, even though like the top row is not zero, right? Or even close to it. I just automatically take like, give me whatever the largest value is, and that's what goes on top, right? And that's why this is all weird like this. And what I'm going to try and do right now live, because I don't think this is part of the code I wrote. Let me actually just showcase you what I had written for forward elimination. There's an extra print statement there that's unnecessary, but that is more or less the same. I had like a commented out section for the same code. The reason this took me so long is because I kept worrying about like a division by zero error that didn't make sense if you did the swap, right? I would do the code for the swap and then once I started getting into this loop here, I'd repeatedly worry about like, oh, what if there's a zero? What if there's a zero? Except it didn't matter because the 0th position would be the current position, like the next row I, not row K. So as long as it wasn't on row K, it would never divide by 0. And if it's 0 divided by 2, well, that's just 0, and there isn't a change in that row, which is fine, and that's what I was worried about, and that's what kind of took me a little too long to get over. And if I had drawn it out or done it on pen and paper, it would have been something I would have picked up on earlier. But anyways, so going back to changing this up live, okay, so here I always check for the max vector, right? So instead of doing this like immediately, what I should do is let me actually just add okay, I'm just gonna move that notification away. We're just gonna add I'm gonna wrap this in parentheses just to make sure there's no weird order precedence stuff that happens, and say and a k equals 0, right? Right. But let's make sure we add an elif to this as well. Elif p equals k, the opposite of this condition over here, this first condition, and a k, and this is not the most efficient way to write this if else, also equals 0. We'll just say raise value error, right? Actually, it's more of an arithmetic error, I guess, because it's a non-solvable system, right? I believe that should fix this. Boom, and we get the expected value 2101, right? Because this, the asserts that are generated here are generated with the mindset that you're not swapping a row unless it's literally a division by 0 error or division by a number so small that it's close enough to 0 and that it's just going to cause a potential landslide when it comes to numerical stability, right? So let's just see if we can run these, because I actually never ran these before. Oh, there's another issue. Copy mat is not defined. Well, there's some test code here that doesn't exist. Copy mat is not existent, so I'll just do a2.copy. Actually, v for v in a2, we'll just go v.copy to make sure. I think that should be fine. Let's see if we have an issue. Ooh, which one is this? This is a try block. Ah. Wait, what? Expected an error on 0 first pivot, but none was raised. Why? I will just swap the rows. Okay, I don't even know this is something that it created an issue with. Okay, let's see what it does with a5. A5 is not a problem, and this is something we've already taken care of. And yeah, we're golden, guys. You know, I'm just... What's row echelon form? A row, it can be obtained as a result of Gaussian elimination. Every matrix can be put in row echelon form. Huh. Every matrix can be put in row echelon form by applying a sequence of for square matrices, an upper triangular matrix with non-zero entries on the diagonal is in row echelon form. And a matrix in row echelon form is weak. Oh, okay, so upper triangular matrices are row echelon forms. Oh, okay. A matrix is in row echelon form if all rows having only 0 entries are at the bottom. Okay. Leading entry, that is the leftmost non-zero entry of every non-zero row called the pivot, is on the right of the leading entry of every row above. Okay. Anyways, I'm just starting to Google and look into row echelon forms. This is interesting. Maybe we can have a bigger discussion about this tomorrow. But yeah, this one, I know I didn't go too much into the Googling and the babbling and all that, because the algorithm itself hurt me a little bit, which is sad. I would like to think I'm better at this than I am, but I'm not, and that's okay. It's how you learn, is by trying, by failing. That's another thing when it comes to all of this, is to never be afraid of failure, because that's just part of life, right? If you're afraid of failure, afraid of asking stupid questions, afraid of asking why to begin with, well, you're never going to go anywhere, right? I think there's a saying, I don't know if this is an actual saying, I just made it up one day, or at least I feel like I made it up one day, but it could actually be a saying, I don't know. But it's like, I'd rather look stupid and ask a question once rather than hold my peace and have to ask a stupid question multiple times. Actually, no, that doesn't make much sense. The point is I'm trying to make is, like, no matter how high stakes the situation is, you might as well ask the stupid question and get the answer. First of all, it might not even be that stupid of a question, and even if it is, just get the answer, because especially if you're in a high stakes situation, you definitely want to know the answer before it becomes even more of a high stakes situation, right? All of this is irrelevant, though. These are all thought processes, tips and tricks, how your mind works and all that. And that can go into a very deep place, but it really has to start with a curiosity and a love for this world. I think that's really what curiosity is. It's the greatest expression of gratitude for the miracles that besiege us. And I believe that. I believe we are besieged by miracles, even in this day and age where everything is unknown. Not unknown, everything is known. Anyways, that's beautiful. As are each and every one of you, and I wish all of you the best of luck in learning whatever you want to learn, even if it means learning how to love. Have a great one, everyone. Bye bye.